Welcome to this video where we'll explore LeetCode problem number 28, find the index of the first occurrence in a string. This is a commonly encountered problem in string manipulation, and we'll be walking through different approaches to solve it. Let's dive in and get started. The problem asks us to find the index of the first occurrence of a substring, called needle, within another string, called haystack. If needle does not appear in haystack, we should return -1. For the input format, haystack is the main string where the search will be performed, and needle is the specific substring we are looking for. The output, on the other hand, is an integer that represents the zero-based index where the needle first appears in haystack. If the needle is absent, the function should simply return -1. This is the core task we are solving here, so understanding the input and output expectations is critical before diving into examples. For instance, in the first example, the haystack is the string sad but sad and the needle is sad. The output is 0 because sad first appears at index 0 in sad but sad. On the other hand, in the second example, the haystack is LeetCode and the needle is Leto. Here, the output is -1 because Leto is not found within LeetCode. These examples showcase the two possible outcomes, either the exact starting index of the needle or -1 if the needle is absent. In another example, the haystack is hello and the needle is ll. The output is 2 because the substring ll begins at index 2 and hello. Now, regarding constraints, the lengths of both haystack and needle are between 1 and 10,000, and they consist solely of lowercase English letters. Additionally, there are some edge cases to consider. For example, the problem guarantees that the needle will never be an empty string. If haystack and needle are identical, the function must return 0, as needle starts at the very beginning of haystack. Furthermore, if needle is longer than haystack, it is impossible for needle to be a substring, so the function should return -1. Lastly, in cases where needle appears multiple times in haystack, we are required to return the index of the very first occurrence. This problem is a classic example of string pattern searching, and while it can be solved using straightforward approaches like brute force, more efficient solutions exist, such as using the Knuth-Morris-Pratt (KMP) algorithm or other optimized string matching techniques. Understanding these nuances will help us design a robust solution. To solve the problem of finding the index of the first occurrence of a substring within a string, we can consider multiple approaches. Let's start with the brute force method. The intuition behind this approach is straightforward: iterate through the haystack string and, at each position, check if the substring starting there matches the needle. For every starting index in haystack, we extract a substring of the same length as needle and compare it character by character. If a match is found, we return the current index. Otherwise, if we complete the iteration without finding any match, we return -1. This method has a time complexity of O, mn plus 1, *n, where m is the length of haystack and n is the length of needle. Essentially, this means that for each potential starting position, we perform up to n comparisons, making it inefficient for larger strings. On the positive side, it requires no extra memory and is conceptually easy to implement. However, the main drawback is its inefficiency due to redundant comparisons, particularly when dealing with long strings or repeated patterns. Now, let's explore a more efficient solution, the Knuth-Morris-Pratt, or KMP, algorithm. The key idea behind KMP is to eliminate redundant comparisons by pre-processing the needle string into what's called a longest prefix suffix, or LPS, array. This array stores, for each position in needle, the length of the longest prefix that is also a suffix. By using this LPS array during the search phase, we can skip over sections of the haystack that have already been checked, saving significant computation time. The process involves two main steps. First, we pre-compute the LPS array for the needle. Then, as we scan through haystack, we use the LPS array to decide where to continue matching after a mismatch. If a match is found, we return the starting index, otherwise, we return -1. The KMP algorithm achieves a time complexity of O, m plus n, where m is the length of haystack and n is the length of needle, as it avoids rechecking characters. While it requires additional pre-processing to compute the LPS array, the benefits in terms of efficiency make it particularly valuable for larger inputs. One trade-off to consider with KMP is the pre-processing step required to compute the LPS array, which adds a small upfront cost. Alternatively, many programming languages provide built-in functions for substring searching, such as Python's strfind or Java's indexOf. These functions are highly optimized under the hood and can be used directly to solve this problem with minimal effort. The time complexity of such functions often approaches O(m plus n), depending on the implementation, and they require no additional space beyond the input strings. This makes them an attractive option for quick solutions, especially in practical, real-world applications. The advantage of using these built-in functions is their simplicity, as they significantly reduce development time and minimize the risk of implementation errors. However, the downside is that they rely on external libraries, which may not always be allowed in certain settings, such as coding interviews. In such cases, demonstrating a manual implementation like KMP is often preferred, as it showcases a deeper understanding of algorithm design. Given these considerations, the KMP algorithm emerges as the most optimal solution for this problem. It strikes an ideal balance between efficiency and algorithmic clarity, making it especially suitable for scenarios like coding interviews where demonstrating problem-solving skills is critical. While the brute force approach is simpler to implement, its inefficiency with larger inputs makes it less desirable. Built-in string functions, on the other hand, offer convenience but lack the opportunity to showcase algorithmic expertise. By choosing KMP, we gain the advantage of linear time complexity and the ability to handle redundant comparisons systematically. The key insight here is recognizing that preprocessing the needle with the LPS array not only reduces computational redundancy but also highlights the power of preprocessing in optimizing algorithms. Although calculating the LPS array adds a small preprocessing step, this cost is negligible compared to the performance gains during the search phase. Overall, KMP is not just an efficient choice but also a well-rounded strategy for solving substring matching problems effectively. In this problem, we are tasked with finding the first index at which a given substring, called needle, appears within a larger string, called haystack. If the substring isn't found, we return -1. For example, if the haystack is hello and the needle is LL, the result would be 2 because LL starts at index 2. Now, to solve this step by step, let's consider a brute force approach. First, we need to understand that the needle must match character by character in the haystack starting from a specific index. Importantly, the maximum index where we can start checking in the haystack is determined by subtracting the length of the needle from the length of the haystack. This is because the needle cannot extend beyond the bounds of the haystack. With this understanding, the brute force logic becomes straightforward: iterate through the haystack from the first valid starting index to the last valid starting index, and check for matches at each step. During this iteration, at each index I, we extract a substring from the haystack that starts at I and is the same length as the needle. We then compare this substring to the needle. If they match, we return the current index I. If no match is found after checking all valid indices, we return -1 to indicate that the needle does not appear in the haystack. To make this clearer, here's the pseudocode. First, calculate the lengths of the haystack and the needle. If the needle is empty, the problem is trivial, and we immediately return 0. Otherwise, iterate through all valid starting indices in the haystack. For each index, extract the substring and compare it to the needle. If a match is found, return the index. If the loop completes without finding a match, return -1. This simple approach ensures that we systematically check all possibilities. Breaking this process down further, there are 2 key operations involved. First, we use substring extraction to isolate a portion of the haystack that matches the length of the needle. Second, we perform an equality check between the extracted substring and the needle. Both of these steps are repeated for each valid starting index. Now, let's consider some edge cases to ensure robustness. If the needle is empty, we return 0 as specified. If the needle is longer than the haystack, it's impossible for the needle to be a substring, so we return -1. Other cases include handling repeated characters in the strings or ensuring that matches at the very end of the haystack are correctly identified. A critical insight here is understanding why we only iterate up to mn+1. Beyond this point, the substring extracted from the haystack would exceed its bounds. As for the time complexity, each substring extraction and comparison costs n, and we repeat this for up to mn+1 indices. In the worst case, This results in a time complexity of O(m*n). In terms of space complexity, the brute force approach is highly efficient, as we don't use any additional data structures beyond the input strings. This means the space complexity is O(1). The algorithm directly processes the strings using slicing and comparisons, which keeps memory usage minimal. However, while this simplicity is appealing, there are trade-offs. The brute force method is inefficient for large inputs because of its O(m*n) time complexity. To address this limitation, more advanced algorithms like the Knuth-Morris-Pratt (KMP) algorithm or the Rabin-Karp algorithm can significantly optimize performance, reducing the time complexity to O(m+n). Despite its inefficiency, the brute force approach is an excellent starting point for understanding how substring search works conceptually. It forms the foundation upon which optimized solutions can be built, making it a valuable step in the learning process. This is the Python solution to LeetCode problem number 28, which is about finding the index of the first occurrence of a substring, needle, in a string, haystack. The approach used here efficiently checks each possible starting index in the haystack for the needle. The function strstr takes two inputs, haystack, the string to search in, and needle, the substring to find. First, we calculate the lengths of both haystack and needle, storing them in n and m, respectively. This helps us determine the range for iteration and check edge cases. There is a special edge case where the needle is an empty string. According to the problem's constraints, if needle is empty, the function should return 0 immediately. This is handled at the start of the function. The main logic uses a for loop to iterate through possible starting positions in haystack. We loop from index 0 to n(m), ensuring that the substring extracted doesn't exceed the bounds of haystack. At each iteration, we extract a substring of length m from haystack, starting at the current index I. This substring is then compared to needle. If they match, we return the current index I as the first occurrence of the needle. If the loop completes without finding a match, it means needle does not occur in haystack, so the function returns -1. This solution works efficiently because it avoids unnecessary checks beyond the valid range of haystack and performs substring comparisons directly. The time complexity is O(n*m) in the worst case, where n is the length of haystack and m is the length of needle. However, in practical scenarios where m is small, the performance is often sufficient for solving the problem. This is the Java implementation of the LeetCode problem number 28, find the index of the first occurrence in a string. The implementation mirrors the Python logic exactly. Key differences include the use of Java's substring method to extract substrings and equals for string comparison. Java explicitly handles variable types, and the class structure adheres to Java conventions. The algorithm iterates over the haystack string and checks for the needle's occurrence using substring matching. If a match is found, the starting index is returned, otherwise, it returns -1. This approach ensures simplicity and readability. To solve this problem, we start with example 1, where the input haystack is the string hello and needle is the string ll. First, we calculate n, the length of the haystack, which is 5, and m, the length of the needle, which is 2. Since the needle is not empty, we move forward. We then begin iterating over the haystack with a loop. Starting at index I equals 0, we extract the substring haystack 0:2, which is he, and compare it with ll. Since they don't match, we continue to the next iteration. At I equals 1, the substring becomes haystack 1:3, or l, which still doesn't match ll. When I equals 2, the substring haystack 2:4 results in ll, which is a match with the needle. At this point, we return the index I equals 2. This means the first occurrence of ll and hello is at index 2, and our final output is 2. Now, let's look at example 2, where the input haystack is AAA and the needle is BBA. Here, n, the length of the haystack, is 5, and m, the length of the needle, is 3. Since the needle is not empty, we proceed with the loop. Starting at index I equals 0, we extract the substring haystack 0:3, which is AAA, and compare it with BBA. They don't match, so we move to the next iteration. At I equals 1, the substring becomes haystack 1:4, which is again AAA, and still doesn't match BBA. At I equals 2, the substring is haystack 2:5, which is also AAA. Since none of these substrings match BBA and we've reached the end of the haystack, we conclude that there is no match. As a result, we return -1 to indicate that BBA does not appear in AAA. In example 3, the input haystack is ABC, and the needle is an empty string. Here, n is the length of the haystack, which is 3, and m is the length of the needle, which is 0. This time, we encounter an edge case. Since the needle is empty, we immediately return 0 without entering the loop. By definition, an empty needle is considered to be found at the very beginning of any haystack, so the output is 0. This concludes the example, highlighting how the function handles the case where the needle is empty. To analyze the time complexity of this solution, let's break it down step by step. First, let's define some terms. Let n represent the length of the haystack and m represent the length of the needle. The outer for loop is designed to iterate over the range from 0 to n m plus 1. This ensures that we only check positions in the haystack where the needle can fully fit. In the worst case, this loop will execute approximately n times if m is much smaller than n. For each iteration of the loop, we perform a slicing operation on the haystack to extract a substring of length m. This slicing takes m time because it involves copying m characters. Additionally, we perform an equality check to compare this substring with the needle, which is also m, since it checks the characters one by one. Combining these, the work done in each loop iteration is m, and since the loop can run up to n times, the overall time complexity becomes n*m. Now, let's consider the best, average, and worst case scenarios in more detail. In the best case scenario, the needle is found very early in the haystack, possibly even at the very first position. In this case, the loop terminates after just one iteration, and the time complexity reduces to m for the substring comparison. In the average case, the needle is likely found somewhere in the middle of the haystack. On average, this means the algorithm performs around half the total iterations, but the complexity still simplifies to n*m, because we're analyzing asymptotic behavior. Finally, in the worst case, the needle is either absent from the haystack entirely or appears near the very end. Here, the loop runs the full n iterations, and each iteration still includes the m substring operation, leading to n*m time complexity overall. Turning to space complexity, the solution is efficient. The input strings, haystack and needle, do not consume additional memory beyond their original storage. The slicing operation creates a temporary substring of length m during each iteration, but this memory is reused, so the peak memory usage remains m. Auxiliary variables such as n, m, and the loop index I use constant space, 1. Therefore, the overall space complexity of this solution is m. This solution represents a naive approach to the problem, and it's worth comparing it to other methods. In a brute force approach, you would use two nested loops. The outer loop iterates through all possible starting positions in the haystack, and the inner loop compares the needle character by character with the substring at each position. This also results in a time complexity of n*m, which is similar to the slicing-based solution we just analyzed. However, more optimized algorithms exist. For example, the Knuth-Morris-Pratt algorithm, or KMP, pre-processes the needle to create what's called a partial match table. This pre-processing allows the algorithm to avoid redundant comparisons when mismatches occur, scanning the haystack only once. The result is a significantly improved time complexity of n plus m in the worst case. While our slicing-based solution is simpler to implement, it's not as efficient as these optimized approaches for larger inputs. Finally, let's reinforce the mathematical reasoning behind the time and space complexity of this solution. The slicing operation, haystack, I plus m, takes m time because it iterates through m characters to create the substring. The outer loop can execute up to n iterations, meaning the total time complexity is n multiplied by m or n*m. On the space complexity side, no additional data structures are used. Each substring is created on demand during the slicing operation, and its memory is reused in subsequent iterations. This ensures that the peak memory usage for slicing remains constant at m. Therefore, the overall space complexity is m. While this is acceptable for small inputs, more advanced algorithms like KMP achieve better efficiency both in time and space, making them preferable for larger problem sizes. In this section, let's look at some common mistakes that can occur when solving this problem. First, one frequent issue in a brute force approach is using incorrect substring boundaries. For instance, when iterating through the string, if you forget that the substring should end at I plus len, needle, you might go out of bounds or compare an incomplete portion of the string. To avoid this, ensure that your loop only runs up to haystack.length needle.length, and double-check how you're extracting substrings. Another common pitfall is overlooking edge cases. For example, what happens if the needle is an empty string? Or if the haystack and needle are identical? Missing these scenarios can cause runtime errors or incorrect results. Always account for cases like empty strings, full overlaps, or very short inputs. Lastly, be cautious when relying on inbuilt string functions like haystack.find, needle, without considering their time complexity. While these functions are convenient, in an interview setting, you may need to demonstrate your understanding of the underlying algorithm. Be prepared to explain or even implement alternatives like KMP or Rabencarp for a more thorough discussion. Now, let's focus on a couple of algorithm-specific mistakes. When implementing the KMP algorithm, skipping the pre-processing step for the partial match table is a common error. This pre-processing is critical because it allows KMP to achieve its efficiency by avoiding redundant comparisons. Without it, the algorithm loses its advantage over brute force. Make sure to carefully implement the prefix-suffix table and understand its role in optimizing the search. Another frequent issue arises in the Rabencarp algorithm, where hash collisions are ignored. It's a mistake to assume that matching hash values always mean the strings themselves match. This can lead to false positives and incorrect results. To address this, always add a secondary check after a hash match to confirm that the substrings are indeed identical. Attention to these details can make a big difference in implementing these algorithms correctly. When preparing for interviews, it's important to approach string search problems with a clear understanding of key concepts. Many of these problems revolve around recognizing patterns within strings. For instance, algorithms like KMP and Rabencarp leverage pre-processing or hashing to optimize performance, and knowing how these techniques work can help you choose the best approach. It's also crucial to understand the trade-offs between algorithms. Brute force is simple to implement but inefficient with its O(n*)m time complexity. KMP, on the other hand, is more efficient at O(n+m), especially for repeated patterns, but it can be challenging to implement due to the pre-processing step. Rabencarp is a strong choice for multiple searches, but you must be wary of hash collisions. Additionally, you should practice explaining time complexity clearly, particularly how pre-processing in KMP or hashing in Rabencarp contributes to the overall efficiency. Finally, always be ready to discuss edge cases, as interviewers often use scenarios like empty strings, overlapping substrings, or very large inputs to test your problem-solving ability. String search problems are foundational in coding interviews, and they often overlap with related challenges. For example, LeetCode 459, repeated substring pattern, tests your ability to identify repeating patterns within a string. LeetCode 214, shortest palindrome, involves extending a string to make it a palindrome and uses KMP preprocessing. LeetCode 796, rotate string, requires checking if one string is a rotation of another, which relies heavily on string manipulation. Lastly, LeetCode 1044, longest duplicate substring, introduces more advanced techniques like binary search and suffix arrays. Alongside these problems, it's also helpful to evaluate alternative approaches and their trade-offs. The brute force method is straightforward: compare every substring of the haystack with the needle. However, it's inefficient at O(n*)m, especially for large inputs. The KMP algorithm, with its O(n+m) complexity, is faster but demands careful implementation of the prefix-suffix table for pre-processing. Each method has its strengths and weaknesses, so understanding these trade-offs is key. Finally, let's examine two more approaches that often come up in this context. The Rabencarp algorithm uses hashing to compare substrings efficiently, with an average time complexity of O(n+m). However, in the worst case, it can degrade to O(n*)m due to hash collisions, so it's essential to include a secondary verification step. This method is particularly useful when performing multiple pattern searches within the same string. On the other hand, Built-in string search functions like haystack.find, needle, offer simplicity and speed, often running in O(n), depending on the implementation. While effective, relying on these functions in interviews may not showcase your algorithmic understanding, which is why it's important to be prepared to explain or implement alternative solutions. Each of these approaches has unique trade-offs, so selecting the right one often depends on the problem requirements and constraints. Great job! You've just learned how to solve LeetCode problem number 28 using different approaches. We reviewed the problem, explored solution strategies, and highlighted key takeaways. Keep practicing, and don't forget to like, share, and subscribe for more coding content. See you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!